Hello, I am Professor Von Schmohawk, and welcome to YU. Today's lecture is on topology. To help with my lecture, I have arranged a small demonstration of my multi-dimensional conformal space projection configurator.
Excuse me, Professor, where exactly would you like me to plug this device in?
Oh yes, AV, just plug it into any of the power receptacles.
Yes, sir, Professor!
Thank you, Mr. Geekman.
Don't mention it.
Yes, class. Your fellow classmate, A.V. Geekman, has graciously volunteered to help me with our demonstration today.
It is my pleasure entirely, Professor. I am always happy to help in the pursuit of the educational process, and I am honored and might I say privileged to have the opportunity to serve you and the class in this
Thank you, A.V. As I was saying, the multidimensional configurator will allow me to demonstrate spaces of various topologies. Now, for this demonstration, I will need a test object.
Professor!
Yes, Hulk Moose Smasher, do you have a test object we can use?
Yeah. Here you go, Professor!
Ouch.
Thank you, Hulk. As you can see, the multidimensional conformal space projection configurator is capable of projecting test objects into space of various dimensions and topology. For our first experiment, we will place our test object in the configurator and set the number of dimensions to 2. This will project every point in the object into a 2-dimensional space. Now we have to pick the topology of this space. I will start with a simple flat rectangular space. This type of space is called Euclidean, in honor of Euclid, the Greek mathematician who first discovered it.
Oh, Professor!
Adrian Scienstein, do you have a question?
Yes, Professor. Who exactly was this Greek eucalyptus fellow? And was he cute?
Well, Adrian, we don't know much about Euclid except that he lived about 300 BC during the Greek Hellenistic period and spent a lot of time at the Great Library at Alexandria, Egypt. He wrote the most successful book in the history of mathematics, entitled Elements. Today, Euclid of Alexandria is referred to as the father of geometry.
I guess he was pretty cute, but he wasn't as cute as some science professors I know.
Yes, Adrian, that may have well been true. Now, where was I? Oh, yes, we will create a Euclidean 2-dimensional space for our test object.
Hey, Professor! You're not gonna hurt my football, are you?
I assure you, Mr. Moose Smasher, that your football will be completely unscathed by our little demonstration. In fact, if you would care to assist me in my next demonstration, I will lay all your concerns to rest. I think you would make the perfect subject for this quest into the unknown.
Gee, thanks, Professor!
Just step into the projection chamber, and I will demonstrate.
Gee, Professor, it's a little tight in here.
Oh, I'm sorry, Mr. Moose Smasher. I will have to expand our 2-dimensional space a little.
Hey, where'd everybody go?
Although we can see him, Mr. Moose Smasher cannot see us because our location in 3-dimensional space does not intersect his 2-dimensional space. However, let's see what happens when an object from our 3-dimensional space intersects his flat space.
Do not attempt to adjust your television and/or computer monitor. This is a message from the American Society of Mathematical Correctness. The scenes you are about to see are theoretically impossible, so do not try this at home. If you were to actually inhabit a 2-dimensional space, everything would appear to you as a line segment. However, this would be boring. So in the interest of higher education and entertainment, the makers of this film have taken artistic liberties during its creation. With that said, we now return you to your feature presentation, already in progress.
What was that, Professor?
Notice that Mr. Moose Masher could not see the ball until it touched his two-dimensional space. Then all he could see was the part of the ball which intersected his space. To Mr. Moose Masher, the ball seemed to appear out of nowhere as a point, which grew into a circle, reaching its largest diameter when the ball was exactly halfway through. As the ball continued on its path through his space, the circle shrunk back to a point and then disappeared.
What was that, Professor?
A three-dimensional cube passing through a two-dimensional space would appear even stranger. In this case, what Mr. Moose Masher would see would depend on the way the cube was positioned as it passed through the plane. If one of the flat sides of the cube intersected the plane first, Mr. Moose Masher would see a square suddenly appear out of nowhere. As the cube passed through his space, the square would remain for a short time and then disappear. On the other hand, if one of the edges of the cube intersected the plane first, Mr. Moose Masher would see a line appear, grow fatter, then thinner, and finally disappear. An even more interesting way that the cube could pass through the two-dimensional space would be if one of the corners of the cube intersected the plane first. In this case, Mr. Moose Masher would see a point appear, then grow into a triangle, then a hexagon, then a different triangle, and finally shrink back to a point and disappear. Now, Mr. Moose Masher, will you please demonstrate what happens when you throw your football test object?
Sure thing, Professor. Ouch.
You see, class, because Mr. Moose Masher is inhabiting a finite, bounded space, the football cannot travel in one direction without encountering a boundary. The boundary is the end of his two-dimensional space.
Ouch.
There are two ways that we can solve Mr. Moose Masher's problem. One way would be to make his space so large that it is essentially infinite.
Quack.
However, that would run up the university's electric bill.
Uh-oh.
But there is another solution to this problem. We can keep the size of Mr. Moose Masher's space the same, but change the topology so that it is unbounded. As an easy example, let's pick a two-dimensional space with a cylindrical topology. A topology is just a particular way of connecting points in space. We call this topology cylindrical because its space is connected in the same way a sheet of paper wrapped around a cylinder connects to itself. Mr. Moose Masher, try throwing your football one more time.
Okay, Professor. Ouch.
Let's have our projector display Mr. Moose Masher's cylindrical space a little differently so we can see what's going on. You see, Hulk's space is connected like the surface of a cylinder, but it is actually still flat. All we have done is to connect the left and right boundaries together so that things in his space can continue to move horizontally without encountering a boundary. Let's look at an instant replay of that last pass to see what happened. Cylindrical space has no boundaries in the horizontal direction, but it still has vertical boundaries.
Hey, Professor. There's somebody in here with me.
Don't worry, class. Hulk is just seeing an image of himself. Just like the football, light rays from Mr. Moose Smasher will travel around the cylindrical space and strike him from the opposite side. The cylindrical space is still finite, but Mr. Moose Smasher sees it as infinite in the horizontal direction. Just as there are no edges to his space, there is no longer a center point.
Hey, think fast. Ouch.
Now, let's try a more interesting topology. How about the spherical two-dimensional topology? Now Mr. Moose Smasher's two-dimensional space is completely unbounded. Although the total amount of space is still the same, he can move in any direction, left, right, up, or down without stopping at a boundary. We say that his space is finite but unbounded. Notice also that Mr. Moose Smasher now appears somewhat distorted. This is because there is no way to map a flat surface onto the surface of a sphere or vice versa without creating distortions. Early map makers were familiar with this problem when they tried to portray the surface of the Earth on a flat piece of paper. If you want to know how they felt, try peeling an orange and laying the peeling out flat on a tabletop. Since Mr. Moose Smasher's space is now completely unbounded, no matter which way he throws the ball, it will always come back from the opposite side of his space. Mr. Moose Smasher, try throwing your test object so we can see what happens.
I don't think so.
Okay, in that case, let's think about what an object traveling in a straight line in a spherical, two-dimensional space would do. Light rays always seem to travel in straight lines, so what would a light ray do in Mr. Moose Smasher's space? We know that light always takes the quickest path between 2 points. On any surface, flat or curved, the shortest path is called a geodesic. This is why airline routes sometimes appear to be arcs rather than straight lines. Notice how on a flat map, the airline route from New York to Tokyo appears to be anything but straight. However, when viewed from the right perspective, you can see that it is actually the shortest path. This is called the Great Circle Route. You can determine the Great Circle Route between any 2 points on a globe by stretching a string tightly between those 2 points. Of course, a light ray in our three-dimensional space would not travel along the surface of the Earth. But no matter which direction a light ray travels in a spherical two-dimensional space, it will always return to the original point from which it started. We call this type of space non-Euclidean because of the distortions which happen to straight lines. Consider what will happen to lines or light rays which start off as parallel. Because they must each follow a geodesic path, they will eventually intersect. In fact, they will intersect twice. Think of 2 longitude lines on the Earth. They start out as parallel to each other at the equator, but eventually cross at the north and south poles. This unusual property of parallel lines in a curved space causes shapes to become distorted. Take, for example, a square. Since straight lines follow geodesic paths, the area of the square will be slightly larger than the same square drawn in normal Euclidean space. In addition, the corners will all have angles slightly larger than 90 degrees. The same type of distortions would happen to a triangle. In flat space, the angles of any triangle always add up to 180 degrees. But in a spherically curved, non-Euclidean space, the angles will add up to more than 180 degrees. These distortions are not just because we are trying to project a curved space onto a flat screen. The distortions will actually exist in Hulk space. If Hulk measured a triangle, the angles would actually add up to more than 180 degrees. Circles will remain circles, but the ratio of their area to their circumference will be greater than in flat space. Also, the ratio of circumference to the diameter will be less than pi. But don't worry, even though the rules you learned in geometry won't work in a non-Euclidean space, the space we live in seems to be Euclidean. At least as far as we can tell.